Welcome to my talk about hypervisor-based analysis of macOS malware. So this talk is going to be more on the defensive side. I won't reveal any new 0 days or fancy new bugs, but instead I want to show you how we can build more sophisticated tools to dynamically analyze macOS malware at scale. So first, my name is Felix Seele, and I'm technical lead at VMware. I'm responsible for the dynamic analysis engine of our malware sandbox. I graduated in IT security, and my master's thesis was about dynamically analyzing macOS malware. So this is basically me presenting the results of my master's thesis, and we're now turning these results into a commercial product at VMware. And we already released the first preview version to our customers in March. So this talk is going to be roughly structured into 3 parts. First, some motivation. Why should we care about dynamic malware analysis for macOS at all? Then we will dive into the technical details and how these hypervisor-based systems work on a more generic versus independent level. And finally, we will get into the macOS specific part, where I'll present some challenges that we encountered during the implementation of our sandbox, which are unique to macOS, how it works, and finally, I will also present some analysis results of real-world macOS samples to demonstrate our solution. So first, why should we care about developing malware sandboxes for macOS at all? Sorry. You probably all know this type of slide, so that's an unwritten rule that every talk about macOS malware needs to have a slide. But instead of talking about how macOS malware has become more sophisticated, I will skip this part and just want to focus on the growing number of macOS samples. So while on Windows there are a lot of different tools, different sandboxes, both commercial and open source, to process a high number of samples, the situation on macOS just doesn't look so good. And as analysts or companies who want to defend themselves against malware attacks, we need better tools that can analyze samples at scale. And these tools should not only rely on signatures like AB, they should be also be able to detect previously unknown samples, which might be used in a targeted attack against the company. So dynamic malware sandboxes are one such tool. And how they work, they execute the sample in a safe and isolated environment, and then try to record, analyze, and trace the behavior of the sample. And finally, they produce some sort of report and a score which predicts how malicious this file is with certain confidence. So let's see how we can build such a sandbox for macOS. First, what do we have purely available to dynamically analyze malware on macOS? So there are many small tools that monitor different parts of the system. You can use tools like ProcProc or BlockInfo or BlockBlock to monitor processes and persistence. There's the dtrace subsystem in the kernel, which you can use to, for example, monitor file system usage or system calls. There are various firewalls to monitor network activity. And of course, as a last resort, you could always attach a debugger and step through the program manually. But what's missing? So there's no generic function call tracer, for example, like the ltrace utility on Linux. And all these tools need to run inside the analysis VM. So if malware gets more evolved, and we already saw some examples of this today, they could easily detect these tools running inside the VM and then only exhibit benign behavior or even try to corrupt the analysis completely. And lastly, this is all, there's no automation involved in all, so this is all the manual process. The analyst has to look at all the different outputs from the different tools and try to come to a conclusion what's happening here. So let's define a set of goals for possible sandbox solutions. So first, we want to have full visibility of function calls at every level. So no matter if the sample does low-level syscalls, some Objective-C calls or C calls, we want to see all the behavior of the sample. And it should be completely isolated and transparent. So the sample should not be able to detect that it's being analyzed, and it should obviously not be able to break out of the analysis environment. And finally, all this should be automatable so that we can process a high number of samples. We need automation, and there shouldn't be a big overhead involved with all this. So let's have a look at these goals one by one. First, the visibility of function calls. So let's have a look at what the system usually looks like. There are many different abstractions layers. Starting at the kernel, we have direct syscalls, we have low-level system libraries, and we have more the higher-level system libraries, which the sample will interact with. For example, opening a network connection and downloading some file, which is a relevant information which you want to track. The sample could do this using raw syscalls, so not by doing any function call at all. It could open the socket, connect, and receive data. It could also use the C-level abstractions of these syscalls, socket and the connect function. It could use the core foundation version, or it could use the high-level foundation Objective-C version of it. So as an malware analysis system, we want to be able to see all these different kind of calls, no matter if the sample does low-level calls, maybe tree date analysis, or if the sample does high-level calls. And we also want to intercept these calls at the highest level possible, because there's, for example, some sandboxes which only intercept syscalls, but then you have a lot more data to process. So there are multiple problems with that. For example, if you do a high-level function call, such as this one, this might result in hundreds of syscalls. So if you only intercept syscalls, you have to infer what the original intent was just by using these syscalls. So it's easier, it's a lot harder to process, it's more data to process, and there are also some user mode calls which don't even result in a syscall. For example, the time call, you can't monitor this using syscalls because it's just user mode. And analysis system needs to be able to cope with all different layers of these calls. So the second goal, isolation, and the third goal, performance. Now, to achieve true transparency and isolation, an analysis system must always run on a higher privilege level than the sample. Otherwise, it will always be able, the sample will always be able to detect that it's being analyzed, hide its malicious behavior, or even corrupt the analysis system. Now, it follows that if you want to analyze user space malware, you need to be at least in kernel space. But if you also want to analyze kernel level code to gain full system visibility, you need to go even one privilege level up, and this is the hypervisor. So I know it's not that easy to run kernel level code on macOS, even for legitimate applications. But very advanced attackers and very targeted attackers could use 0 days, stolen certificates, or vulnerable existing kernel extensions to achieve kernel level code execution. So if you really want full system visibility, you need to go in hypervisor. And yeah, regarding performance, so emulators would be another possibility to implement this, because if you emulate the system, you obviously have full system visibility, but they're usually really slow and not suited to emulate the whole operating system. They're maybe suited to analyze or emulate a single program, but not the whole operating system. But luckily, the hardware system virtualization has been improved in recent years a lot. So with technologies like Intel VTX or AMD, there's only a small performance overhead involved for running VMs. Now, the question remains, how can we use this? How can we use virtualization to do malware analysis? How can we instrument the hypervisor for malware analysis? For this, we use a technique called two-dimensional paging. And we're going to explain this now, but first, let's have a look at traditional paging, traditional address translation first. So every time the CPU needs to fetch some memory from virtual memory address, this needs to be translated to a physical address. So to do this, the operating system sets up so-called page tables. On 64-bit, there are 4 levels of page tables, and these are used to translate the virtual address to a physical address. Now, there's a lot of information contained in these page tables, and this is a very high-level and simplified overview. But one of the metadata which is contained here is, for example, the access permissions. So the memory page pointed to by this page table entry is mapped as readable and executable. So if the sample tries to execute code from the memory page, the MMU will perform the page walk, check the permissions, and yeah, works out because it tries to execute executable code. So that's fine. Now, if we change this, for example, to be just readable and writable, which is the default for example, the data section of a program or a heap, now if the program tries to execute memory in such a region, the MMU will recognize that this is an access violation, and this will result in a page fault. Control will be transferred to the kernel, and the kernel will most likely kill your program. So this is what you usually get when your program crashes with a segmentation fault. This is what happened. Now, in a virtualized environment, we have the virtual machine, and it does exactly the same thing. So the guest OS inside the VM doesn't even know and doesn't even need to know that it's being virtualized. It just uses the same page tables, sets up the same page tables as before, and it translates its guest rich memory addresses to guest physical addresses. So why guest physical and not physical? Because VMs can't be allowed to access memory of the host directly, because if they could potentially also change memory of the host, or they could change memory of other VMs running on the same host. So for this reason, to isolate the VMs from each other and restrain them to their set of memory, we apply the same technique again. And these are called the second level page tables, and that's where the name two-dimensional paging comes from. So we do the same thing which we did before to isolate processes from each other, to now to isolate VMs from each other. And these second level page tables are maintained by the hypervisor, and they're used to translate the guest physical addresses, which the guest VM uses and only knows, to the host physical, to the final memory location. So it's like basically the saying, you can solve every problem in computer science by applying another level of indirection. This is exactly it. So we're just isolating the VMs by applying the same page tables again. And these page tables look very similar, the second level page tables look very similar to the original page tables. They also have permission bits. So in this case, the memory page is mapped readable and executable in both of the page tables, so everything is fine. But again, if we modify the page table permissions in the second level page tables, and the sample tries to execute code in the region that we just changed the permissions on, this will trigger a page fault, but this time in a hypervisor. So this will cause a VM exit, and the respective handler in the hypervisor will be called to handle this violation. And what this allows us to do is that we now know, okay, the sample inside the VM tried to execute code at a very specific code region. So we can intercept execution and get info into the VM just by modifying the outside data structures. So these are the second level page tables are not visible for the guest VM. The guest doesn't know that they are there, and also the guest VM is not notified of the violation. It's only going to the hypervisor. This is completely transparent for the guest VM. So now if we're in the hypervisor, we see, okay, this program tried to execute code at some region, some code page. We can now do something with this information, and then we set the page to be executable again and just continue execution. And the guest inside the VM will never know that this has even happened. So how can we use this for malware analysis or to monitor programs in general? Now, let's go back to the previous example. This is like, let's say this is the virtual address space of a program, and we divide this address space into two sets. So in the first set A, let's call it set A, we put the executable that we want to analyze, and in the second set, all the different system libraries, the kernel, and everything else basically is contained. So now we ensure that at each point in time, only one of these sets is executable. And for example, at the beginning of the analysis, we want to set the sample to be executable. So the center might do some initialization, unpacking, deobfuscation. It might even do like some really sophisticated things that we've seen this morning to unveil its actual code. But we're not really interested in that. We don't really care what it's doing internally. We only care about as soon as the sample does some function calls. So as soon as the instruction pointer leaves this executable area, it will result in a page fault in Hypervisor. And from the Hypervisor, we can now have a look into the system to see what's going on, what function was called, maybe extract the function parameters or something, and then we can resume execution. And also, if the sample uses some parameter string obfuscation, we are not concerned with that at all, because at the time when it calls a function, the strings must be deobfuscated for the library to read the string. So it can be as complex as you want. As soon as the function, as the sample does the call, it needs to be deobfuscated. So we basically can generically defeat all these techniques. And now, when we detect this transition, we switch the sets. So now the set B is executable. These libraries may do some internal calls, maybe you do syscalls. Again, we don't really care about what happens inside. We just care about the transitions between these sets. So as soon as the function has done its work and returns to the sample, we will have another execution call. And now we can extract the return value and continue execution, and the same thing happens, like starts again from the beginning. And this works very generically, and also, of course, if the sample does calls to a low-level library, or even if it does direct syscalls, it doesn't matter. We will always catch these transitions at the highest level, so at the first transition when the instruction pointer leaves the sample. So in theory, this is a very simple approach. It was first presented by Carsten Wilhelms and Ralf Hund, the founders of the VMware. It's simple but very effective, and it provides complete isolation and transparency, because there are no modifications necessary to the guest OS at all. So it runs completely unmodified, no agent, no hooking, and it's unattackable even from the kernel of the guest. So we could analyze, in theory, kernel code of this. Also, it's very efficient, since these calls are intercepted at the highest level possible, so we have less overhead as possible. And also because we intercept the calls at the highest level possible, as I said, this will preserve the high-level semantics, and it will also simplify the analysis which we do on the calls after that, because we don't have like hundreds of syscalls where we need to infer what the sample actually did. We know, okay, it did a call to data in the context of URL, for example. So this makes the analysis, the automated analysis especially, really easy. Okay, now let's say we have stopped execution at some certain interesting point in time, and the next thing we want to do is gather information about what's actually happening inside the VM. And virtual machine introspection is the process of reconstructing the state of the guest VM from the outside. Because remember, we're not running inside the VM, we can't execute any code. The only things we see is memory from outside and maybe some register state, so the state of the CPU. We can't execute code. So everything must be done just with using memory access. And yeah, let's suppose we have suspended execution, and we now want to look into the system, what is happening. This is a bit like maybe memory forensic analysis, where you analyze the physical memory dump, and you want to see what's happening inside, but only that this has to be done in milliseconds at most. So we have to be really fast and really efficient to do this. Now, one of the first things that you want to monitor are processes. So if you have suspended execution, you want to know what process is currently running. For this, you need to know the internal kernel structure. So you need to know where the kernel stores the pointer or whatever to the current process. You need to know how the process structs internally are laid out, where to get the process ID, where to get the process name, and so on. You also need to be able to monitor process switches. So this can be done, for example, by monitoring writes to the CR3 register, because every time the operating system switches the process, it needs to write a new value to the CR3 register. So now that we know what processes are running on the system, the next step is to look what the virtual address space of these processes look like. So because we need to set up this transition monitor, we need to know the memory locations, that's why we need to parse memory address space of the processes. And I hope you all listen closely to Ian yesterday. This is exactly the same thing that he showed, the mmap subsystem. So we need to parse all these VM maps, the VM map entries, and so on. And then we know where in the address space the libraries are located, and we need to figure out which libraries are located where, so we need to identify them. Then we can set up the transition monitoring, and then we can catch these module transitions. And what we need to do now is we need to get, for example, the offset into the library to retrieve the function it was called, and we also need to extract the parameters of the function. These techniques basically apply to every OS and every architecture, only how to retrieve this information and where to find it will be different depending on the OS and the kernel. But on top of this, every operating system also has some unique features which are specific for this operating system and require some special handling. And this is what I want to focus on in this talk. So I don't want to bore you with all the details and all the basics. I want to focus on two specific challenges that we encountered, which are very specific to macOS, namely the monitoring of Objective-C function calls and inter-process communication using the XPC. Okay, let's go into the first one. So let's say we have set up all the monitoring, we know where lines are located, we have a transition or it's execution fault, and by looking at the offset, we have determined that this is a call to NS-string write to file. So this is from an analysis standpoint, this is a really interesting function because we are interested in file writes and we want to know which string was written to which locations. So how do we get the parameters to this function call? We have to look in the register. So this is a instant method. So we see we get the pointer to the object in RDI. Then in second register, there will be the name of the method, which we're not interested in, and the arguments will follow in RDX, RCX, and so on. So now we know where to get the pointers, but how do we get the string? Because this is not C string, we can't just follow the pointer and read memory. For this, we need to reconstruct the internal layout of these objects. So we need to know what a string looks like internally. And to do this, we first have to know, or we have to be sure that this is actually an string. And you see the function prototype says in a string, you need to pass it in a string. But can we trust this? Definitely not, because technically, in a string doesn't even exist. So there's this is called a thing called class clusters in Objective-C. So as a developer, you work with a string, but internally, the runtime of the libraries, they will give you different instances of different classes depending on what the content of the string is. So for example, if you work with paths, then you probably get an NS-pathStore object instead of an NS-string object. And also, since this is object-oriented programming, we might have functions which have protocols as arguments. So basically there, you don't care about what the actual class is at all. You just need to be sure that your object behaves as expected by the protocol. So when we want to analyze this dynamically, we need to determine the class at runtime, because we can't know in advance what will be put, or what will be the parameters for these calls. So how do we do this? Let's suppose we have this pointer, which we know points to some kind of string object, but we're not really sure what class it is. If you follow this pointer, every object is represented by a struct internally. So as you also maybe already know from yesterday, the first and only member of the struct is the ISA pointer. And if you look at this pointer in the debugger, it might look odd because this doesn't look like a valid address. This is because the Objective-C runtime actually uses some unused bits in the ISA pointer for reference counting and some other attributes. So if you want to get the actual pointer to the class struct, you need to apply a mask, and then this points to a struct Objective-C class, which is also inheriting from object, so it also has the ISA pointer, but most importantly, it also has a pointer to a class read-write struct. And this read-write struct has a pointer to a read-only struct, and this read-only struct has a pointer to a string. And this tells us, okay, now this object is actually an NSCF constant string. This is, by the way, also the same thing that simplification libraries do, or that the debugger does, to figure out the class of objects. But if you want, but remember, we are still in the hypervisor, so this must be really fast, and we don't want the guest to notice any delays. So this requires us to follow 4 different pointers and read a string. So that's not really efficient. We need to find a better way to do this more efficiently. And yeah, actually there is a better way. If we go back to this point and look closer at this pointer, look where it points. So it actually points to the data segment of the core foundation library, which implements the NSCF constant string class. And if we look at the symbol table of this binary, we will see, okay, this offset actually points to a symbol, Objective-C class underscore NSCF constant string. So yeah, this is really nice. So we can just by following this pointer and looking at the symbol table, we can determine really quickly that this is an NSCF constant string. This requires some pre-knowledge, so we need to know the data segment, the location of the data segment in memory, which is not that trivial because the data segments are all contained in the shared cache. This is a huge binary blob of about 600 libraries, and you need to load the location and the location of the different data segments within this cache. But if you know this and you calculate the offsets in advance, you only need to follow one pointer, compare it to some pre-computed values, and then you know the class. And yeah, the next step is, now that we know what class this object is of, we still need to get the actual value, we need to get the string. So for every class, or for every class that we want to be able to extract from the hypervisor, we need to implement some mechanism to get the string, or to get the value. And this means that we have to reverse engineer the internal data layout of these classes for all the core foundation classes. This is pretty straightforward because they're open source, and so you can just look inside them, how they store the data internally. You need to implement some logic, and then finally you'll be able to retrieve the string from the hypervisor. And this needs to be done for every single class that you want to extract, because the layout is different. To automate this, maybe it's an idea for the future. Maybe you can use the Objective-C IVA information to get information about offsets inside these class structs automatically, and to automatically extract some values. So, but let's look how this looks in practice. So this is a small sample application. I wrote test my implementation. It just retrieves the current process ID, the current username, constructs a path, and writes username to this path. And now, if you look what this looks like in the analyzer, I hope it's large enough, and I can also try to zoom in a little bit. Okay, so we see that all the strings were basically extracted perfectly. Here we see the return value of the process ID. We see all the object addresses. We see the return value of the username. The path construction was reconstructed properly. And yeah, we also see the write to the file in the end. If you look really closely, what might look weird is this pointer address. So this doesn't really look like valid pointer. It's an odd number, so the least significant bit is set. And this is actually tagged pointer string. So Objective-C uses some optimizations. If you have really short strings, like this is the username, it's just 6 characters long, you will actually put the value, instead of constructing a whole new object for the string, it will put the value directly in the pointer. So we also need to be able to handle these specific things. But yeah, overall you see that it basically resembles the code one by one. The only thing that's missing are the format string arguments, but you could easily add this if you pass a format string. Now let's go to the second problem, the inter-process communications. So as we already heard from Linus yesterday, reverse engineers and security researchers love looking for bugs in IPC because it's really, really complex and used by many components of macOS. So if you want to know more about this, I recommend a talk by Ian, which is linked below, where he goes into the detail of all these different XPC IPC mechanisms. Today I want to focus on XPC and XPC-based remote procedure calls. Why? Because they are basically used by every sample, either explicitly or implicitly, because they many common operations on macOS are implemented using XPC. So for example, for persistence, installing or controlling launch daemons and launch agents is done using XPC. You can also launch processes out of the context of your own process using XPC. This is, for example, what the Open utility does. And you can also do remote procedure calls using NSXPC. And so we need to look into this because if your dynamic malware analysis system doesn't support this kind of communication, doesn't monitor it, it will miss some critical behavior. Now let's look at some examples. First for persistence. So this is the OS complex malware. This is a really, really common pattern for many samples. They first will drop an embedded binary, or they will copy itself to some hidden location, for example, a hidden folder. By the way, these logs are also taken from the analyzer directly, so some more examples how it looks like. Then they will place the previous definition of the launch agent in the specific folders for launch agents or launch daemons. And finally, they will start and load the launch agent using launch control, usually using load and -w. So how is the XPC involved here? So it turns out that for dynamic malware analysis systems, why do you need to detect this? Because if you miss these persistence techniques, miss persistence patterns, you will miss all the behavior of the sample basically, because it could just do all the behavior in the launch daemon and just use the original binary to start this launch daemon. So the lazy approach would be to just monitor launch control implications because all of the samples currently use it. However, it turns out that you don't have to use launch control to install and load your daemon. Because launch control uses XPC to talk to launch D, load the daemon, and since every process can talk to launch D and every process can use XPC, you can actually implement this yourself. So this is what Jonathan Levin did with his launch launch CTL tool. So you can implement the same XPC messages that launch control does to do it yourself. So this is also the function log from launch control. You see it creates an XPC dictionary, sets some values in the dictionary. On the bottom, it sets more important subsystem and routine values, and it also passes the path to the launch agent file. So if you want to be more stealthy and you don't want to use launch control, you can just basically copy these commands into your program and do it yourself without starting launch control. But wait, since XPC is really just an abstraction above math, if you want to go extra stealthy, you can also use raw math messages. So you could also implement these XPC layout, implement the XPC creation yourself, and then you could actually create or install a launch agent just using raw sys calls. You don't need to do a single function call. So as a malware analysis system, you really want to go down and monitor messages on the math level. So what's also really nice, you can instruct launch D to launch arbitrary processes with arbitrary command line arguments on your behalf. So this is what the open utility does, or launch services framework. And these will be spawned as a child of launch D. Why is this important? Because many malware sandboxes just work by looking at subprocesses. So if you have a monitor process and this process spawns a subprocess, the subprocess will be spawned as well. But the subprocess will be monitored as well, sorry. But now, since this new process is a child of launch D, it looks like every other process to the monitoring system. So you need to be able to detect these calls and detect that this happened, this was caused by the sample. And again, to do this, you can use XPC messages. So this is what the XPC message for this looks like in the JSON-like form. You have the similar structure with different routine and subsystem values, and you have an additional dictionary where you pass the parameters for your launch for your launch struct. So the parameters there are, I think they're exactly the same as in the launch agent definition. You just have to add the launch only once key, and then launch D will happily start your program with the supplied arguments. Yeah, and if you don't monitor these calls, your analysis system will miss this invocation, so it will be evaded by the malware. Then, even more convenient from a developer's perspective are remote procedure calls using XPC connection. So this is a feature offered by Apple, which allows developers to outsource potentially dangerous operations from their main binary to external services. So if you have a system daemon running as root, you maybe don't want to process untrusted user data directly in this daemon. And then you can create a helper process which runs on a lower privilege level, which is maybe sandbox isolated, and these will communicate using, again, using XPC. And these helper processes are also launched by launch D on demand as soon as you call one of the methods in the remote object. And again, they will also be child processes like launch D. This is what the code looks like. It's not really important, but it's really easy from a developer perspective. You just call a method on a remote proxy object, and it basically looks like you're just calling a local object, but in fact, it's using XPC to communicate to the header application. This is what the XPC message looks like. So this is just one of the messages. There are multiple for setting up the connection, but this is the one that actually does the invocation. So there's this mysterical F argument, there's a data argument root, proxy number, the signature which the application expects to reply back, and the sequence number. And so this data object, this is the serialized invocation in an undocumented format. So this is a plist, but there are different binary plist formats. Some of them are documented. This one is not. It's not really hard to reverse this, but yeah, in this data blob, there are contained the method selector and the arguments to the function call. So again, let's have a look what this looks like in the analyzer. We see the call to remote proxy object, and then the call to some NSXPC method. And at this point, we detect that there was an XPC message. But we extract the method selector from the invocation from data blob, but we don't know the process name yet. This is because internally in the XNU kernel, the math ports are already set up in the sending process, but not in the receiving process. So there's actually no receiving process yet because it's not yet launched. As I told, it's going to be launched by launch B on demand. So we are waiting for this. Then we see that. Oh, sorry. So at some point we see that launch B started a new process. And we now can resolve this math port, and we see, okay, that the target process name is XPC downloader, and we now know that, there was an XPC call from our sample to this target process, so we need to monitor this target process as well, because it may have some malicious activity. So again, if your analysis system doesn't know how to monitor these XPC calls, you can easily be evaded using this. Okay, finally, let's have a look at some real-world malware samples. I chose the code root remote access Trojan for this. It was discovered by Patrick a few years ago, or 1 year ago, I think. Why I choose it is it's written in Pascal, so it's not that easy to reverse engineer. It's not hard, but it's also not that pleasant. And it has many capabilities. So it can do many file operations, it can list kill processes. Unfortunately, it cannot spawn processes because at least in the version that I had, this wasn't implemented. But yeah, we can download to and from the victim, and most importantly, and most interesting, you can do keylogging and remote desktop, so getting screenshots from the victim. And since the command and control server is down, and this is dynamic malware analysis, so we need to trigger the behavior to be actually able to see it. I wrote my own C2 server to trigger all the different functionalities and to see what it looks like in the analysis. So let's have a look. This is the process core graph. Only by looking at the process graph, you can already see some interesting features. So you can see the security of Trampoline. So this is an indicator that it uses the authorization APIs, executable privileges, to do privilege escalation by asking the user for his password. But yeah, as you also have heard already many times, this probably will work because users are trained to enter their password and click OK. So it tries to persist these privileges by adding itself to the accessibility database to allow for keylogging, and it also installs a launch daemon using launch control. Then let's have a look at the keylogger component. So the keylogger is started even when there's no command and control server connected, and this is already known. So there are a lot of blog posts about this. Patrick already wrote his own keylogger based on this. So I was just curious to see how it looks like in the analysis log, and we can see it creates an event tab. If you wonder about the SL prefix, this is just Skylight, the renamed core graphics framework. So this is actually CG event tab create, and it specifies a mask to monitor for keyboard events. Then adds the event tab to a run loop, enables it, and starts the run loop. And on every key press, it uses this event get integer value field method to get the key code that was entered and converts it to a string. And finally, this string is then written to a log file in a temp folder. So you can really see all the relevant function calls pretty easily in the log here, and yeah, very easy to analyze using this. Then let's look at the remote desktop feature. There's no analysis on this one. It probably isn't a big deal, but I just was curious which method that they use to get the screenshot of the image of the victim. And it turns out they're also using core graphics functions, so they get the main display and then use display create image to get the image of the display. Pretty easy. And then they open another socket to the C2 server and send the data to the C2 server. So actually, if you look at the timestamps, this happens before the screenshots. So it actually works like you send the malware package to start remote desktop, then it will open a secondary socket to the server, and then every half a second it will take a screenshot and send this screenshot over the socket. And see there are 2 cents, and this one has a pretty large buffer, so we would think that this is the image. And if we look into the data, yeah, there's some JPEG magic, so this is probably the image. Cool, so wrapping things up, what did we learn from this talk? First of all, there's steadily increasing number of macOS malware samples, and we need better tools to perform automated analysis in order to protect our companies and customers. And malware sandboxes, which run completely automated and can analyze the behavior of a sample, are one such tool to do this. And by using hypervisor-based techniques, we can achieve full system isolation and at the same time monitor every single function call at the sample did. And we use two-dimensional paging mechanism for this that requires no modification or hooking to be guessed. We just modify external data structures. Yeah, and finally, to perform virtual machine introspection, we need a very in-depth knowledge of the macOS kernel and the operating system in general. And finally, we took a look at some of the macOS specific challenges for dynamic analysis, most importantly, Objective-C function calls and inter-process communication, which can be used to evade dynamic analysis systems. Okay, so thank you all for your attention. If you want to know about our sandbox, see more examples, feel free to come to me after the talk. And yeah, thank you.
Thanks, Felix. We have time for one question. Yes.
So one of the problems with VM detection, I mean, this is all really cool. It's just one of the problems with VM detection is if you're too predictable, then they just fingerprint your VM and then your sample knows to not misbehave. Do you have anything built in, or do you have plans to make your VM unpredictable so samples can't do that?
Yeah, we already have built this in our Windows sandbox. It's already very, very proof. In macOS sandbox, we are also catching up. But yeah, basically, since the sample has to get this information from the OS at some point about, for example, number of CPUs or the disk serial drive or whatever, we can always take these responses and or also modify them on the hardware level so that we don't even have to fake anything. It's all there. So I think our Windows sandbox is really advanced in this. We have a lot of detections built in.